In this video, I'm going over the Project Euler problems numbers 12, 21, and 23 that I covered it when I was doing my practice stream. These problems all share the theme of counting divisors or summing divisors of an integer, so I wanted to group them together. So let's take a look at these. The sequence of triangle numbers is generated by adding the natural numbers. So we've done triangle numbers. We know where triangle numbers come from. Let us list the factors of the first 7 triangle numbers. 1, 3. You mean the divisors? They said factors, but I think they mean factors as in the non-prime factor sense, I guess. So the divisors and factors could mean the same thing if that's what how they're using it. Yes, we can see that 28 is the first triangle number to have over 5 divisors. Yes, 28 has 6 divisors. What is the value of the first triangle number to have over 500 divisors? So to solve this problem, I need to figure out how to compute the number of divisors for any given n, where n is a positive integer, right? So the first thing I decided to do was to sit down and write down a table comparing n and d, where d is my value for the number of divisors, just so I can start pattern hunting. Next, I'm writing down observations as they're coming to me from staring at the table until they build up to a full sort of expression for the function d. So the first thing I notice is that obviously whenever n is greater than 1, you're going to have at least 2 divisors because 1 will divide n and n will divide n, and since 1 and n aren't the same, you'll get 2 divisors just from that. Then I notice that if n is any prime, you'll get exactly 2 divisors because you'll have 1 divides n and n divides n. And since nothing else can divide n, since we said n was prime, those are the 2 divisors. Then extrapolating from that, I notice that if n is some prime power, so it's, a prime by itself, but multiplied by itself multiple times. So 2, 4, 8, 16, or 3, 9, 27, or whatever, one of those numbers. Then that power, if it's p to the r, as I wrote down here, then the number of divisors will be r plus 1, because you have 1, you have p squared, all the way up to p to the r. So that's r plus 1 different divisors that you will have in those cases, and it can't have any other divisors because it can only be divisible by p and the powers of p. So after that, I then look at some examples. I look at 6 and 12. These are examples of numbers that have more than one prime factor. And then I sort of notice and come together the final pattern, which is that when n can be written as a series of prime powers, in other words, when we look at the prime factorization of n, and we take all the powers from the prime factorization of n, then d of n is just, r sub 1 plus 1 times r sub 2 plus 1 times r sub 3 plus 1, and so on through all the powers in the prime factorization. And that gives us a way to compute d from n without having to scan all the numbers between 1 and n. So that gets me part of the way there, but I still need some kind of way to get access to that information contained inside the concept of a prime factorization. So for that, I'm finally going to build a factorization table. But before we get into the programming for the factorization table, I did notice one other thing that I could do in this problem to explore ways to simplify the computation that needs to happen, which is that we're not taking the count of divisors for arbitrary n, we're taking the count of divisors for triangle numbers. So I wanted to take a minute and explore what that looks like in particular, because we know a little bit about the structure of triangle numbers, and that they are sort of the multiplication of 2 other numbers, and so that means that counting their divisors might break down in an interesting way, and it turns out it will actually work, because the count of divisors, if we look at the way it works, it's using these powers of the primes. And so if 2 separate numbers are multiplied together to create an input to that d function, and that those 2 input numbers that we're multiplying happen to have no prime factors in common, then we could actually just multiply the separate computation of d of n and d of n plus 1, or whatever the 2 sources are. In the case of the triangle numbers, it's d of n and d of n plus 1. So that gives us a way to actually do less total compute, because we're not going to have to factorize
the triangle numbers, we're going to factorize n and n plus 1. And of course, as we're going through all the triangle numbers, we will only have to factorize one new number at each step, since we will have one of those two, n plus 1 from one stage will become n of the next stage at each iteration through this process. So that's another trick we're going to use to optimize this. Finally, before I started programming, I wanted to think through the actual computation that I would do to compute D. And the reason I wanted to think this through is so far I've sort of planned out how I would have enough information to compute it in a relatively reasonable way, but I haven't actually been realistic about how much information processing that's going to take. The assertion I've sort of made is that I can take an n and build a prime factorization from it, and then use the prime factorization to compute D. But if I actually just literally make a data structure to contain all of the information in the prime factorization, I'm going to end up doing a lot of extra work, allocating this sort of loose structure that I don't know how big it's going to be up front, iterating it again, and throwing that temporary thing away all the time. And so instead, I want to see if I can sort of glue the constructor and then the reader of that intermediate into one path and eliminate the need for an intermediate. And it turns out that that will work. I just have to build a loop that pulls out one factor at a time, find out the power of that particular factor in one step, and then accumulate all the knowledge from those powers into one result as I'm going. And then, repeat that, taking the next factor that's left over until the sort of n that we started with gets whittled all the way down to a 1. And in this way, I never actually have to build the prime factorization. I just sort of let the information about the prime factorization flow through the code.
Let the function d of n be defined as the sum of proper divisors of n, numbers less than n which divide evenly into n. If d of a equals b and d of b equals a, where a does not equal b, then a and b are an amicable pair, and each of a and b are called amicable numbers. For example, the proper divisors of 220 are 1, 2, 4, 5, 10, 11, 20, 22, 44, 55, and 110. Therefore, d of 220 is 284. The proper divisors of 284 are 1, 2, 4, 71, and 142. So d of 284 equals 222. And that makes, they didn't say this, but I'll throw it in there, that makes 220 and 284 an amicable pair, and they're both amicable numbers. Then it asks, evaluate the sum of all of the amicable numbers under 10,000. So again, I'm trying to find a closed form way to compute this function. I'm going to again call it d, even though it's a different function from the one we did in the first problem I looked at, but I'm calling it d again. And this time it's the sum of all of the divisors that are less than n. So for instance, if 12 is the number we're looking at, then 1, 2, 3, 4, and 6 are proper divisors. 12 is also a divisor of 12, but it's not a quote-unquote proper divisor. So we're looking at the sum of all the numbers other than 12 in that particular case. Like with the previous problem, my instinct is just to start by looking at a table that shows n and d side by side so I can start pattern hunting. And right away I notice that it's going to have a lot of similarities to the stuff from the first problem. The number 1 is unique, the primes are all unique, and the powers of primes all have an interesting property. Now, what the actual computation is for the power of a prime gets a little bit more complicated, and I spend a little bit of time here coming up with the pattern and then looking for a proof that sort of reinforces my suspicion that that pattern will hold. And once I found that, I feel like I'm starting to get somewhere. But as it turns out, after staring at it for a little while and
thinking through a few examples of numbers that aren't just powers of primes like 6 and 12, I just wasn't obviously spotting a pattern that was going to be super easy. So I wanted to take a quick minute to think it through from a different perspective and see if it would make more sense as a table building problem, kind of similar to the sieve algorithms. But as I looked at that, I started running into very similar problems. I just couldn't find anything that was any better than literally scanning all the numbers and testing them directly. And I'm not happier doing it in a table just because it's reusable, because for this particular problem, we really don't need that many numbers in the table. And it seems like it wasn't breaking down into anything simpler than what would have happened if we hadn't built the table. So I felt like I was missing something either way I looked at it for a little while. Then I thought it might be more useful to look at the values of d in a slightly different way. So instead of comparing n directly to d, which is the function I actually want to compute, I thought about writing down n with the list of all of its divisors to see if maybe there was some like set relations between things that I could latch onto that way, and maybe the pattern then would jump out, and then I could do a little bit of math to wrap that up into a simpler closed form thing after the pattern became clear. So I wrote that thing down, and that was the perspective I needed to actually make a new insight, which is that I was kind of looking at the wrong problem. I was looking at the sum of all the proper divisors, and it occurred to me all of a sudden, staring at these patterns, that it would be slightly easier to compute the sum of all the divisors, including n itself. So if you remember, I was saying the proper divisors of 12 as an example, don't include 12, but the list of all divisors is only different because it includes 12. That's the only number that is in the list of all divisors of 12, but not in the list of proper divisors of 12. And it turns out that if you include that one last number, all of a sudden, all of these lists become sort of nice, easy to represent grids that are generated by the prime factorizations. And the sum of all the numbers in that grid is going to be our answer with an extra n included. So if I can compute the sum of all the divisors in total, I can subtract out n afterwards. And this is a thing that's sometimes a subtle and difficult thing to get your head around when trying to solve an algorithm, or like come up with an algorithm to solve a problem, which is that the data transformation you actually need that is useful might not be quite as easy to compute as something very slightly tweaked. And it might be possible to decompose a slightly different representation of the problem and then do a small amount of extra compute to get from the sort of more easily composable, decomposable concept to the thing you actually want. So what we end up with here is a plan where I'm going to use something very similar to what I did when I was counting divisors, where I'm going to rely on the prime factorization. I have to accumulate them in a more complicated way using that thing I figured out when I discovered how to compute the function d for a prime power. And then once I can compute the function for each prime power in the factorization, I accumulate them up and return them, and then at the end, subtract out the extra n for this particular problem. So with all that together, we have a plan for how to proceed, and we're ready to go into the programming.
A perfect number is a number for which the sum of its proper divisors is exactly equal to the number. For example, the sum of the proper divisors of 28 would be 1 plus 2 plus 4 plus 7 plus 14, which equals 28, which means that 28 is a perfect number. A number n is called deficient if the sum of its proper divisors is less than n, and it is called abundant if the sum exceeds n. As 12 is the smallest abundant number, with 1 plus 2 plus 3 plus 4 plus 6 equals 16, the smallest number that can be written as the sum of two abundant numbers is 24. By mathematical analysis, it can be shown that all integers greater than 28,123 can be written as the sum of two abundant numbers. However, this upper limit cannot be reduced any further by analysis, even though it is known that the greatest number that cannot be expressed as the sum of two abundant numbers is less than this limit. It's an interesting comment. I don't exactly know what it means, what mathematical analysis means, but anyway. Find the sum of all the positive integers which cannot be written as the sum of two abundant numbers.
So that comment in the problem was a little weird to me, but after thinking through it for a little while and trying to figure out what exactly they were talking about, I think what they were getting at is that there's no elegant, known mathematical way to create a short description of the maximum number that cannot be represented as the sum of two non-abundant numbers, right? So the hint it's trying to give is that there's not going to be any way to solve the problem except by brute force. At least that's the way I'm interpreting it. And we don't have to 100% brute force all of it because we have tools for getting the sum of the divisors and the sum of the proper divisors, which is what we'll need to test if something is an abundant number. So we can create a list of abundant numbers up to that limit they gave us. And then we can generate a bunch of sums off of the pairs of those numbers and then figure out which one is the highest number that we can't generate with that method. It's not too hard because there's a sort of a small upper limit there that we are given so that we can constrain the amount of n squared combinations we actually have to check here. But I don't really know how to interpret the stuff in the problem talking about mathematical analysis, and the upper bound is known to be lower than what can be shown by mathematical analysis. It's a little bit of a strange phrase, and I think the only thing they could possibly mean is that the work of brute force, just checking each number, is the shortest description known to prove the upper bound. And so you're not going to find a different, more elegant, shorter description than just brute forcing it up until this limit that they gave you. So I just go ahead from here and use the tool we already have for getting the sums of divisors and apply it to this problem. And it doesn't take too long to come to a solution using brute force on the rest of it.